for generators, a set of generators, so the elements and their inverses. The assertion is that there exists a G and G such that, well, the distance from, this is the hyperbolic distance. We talked about that on Monday. It's given by the minimum of the integral of all the paths between the 2 points of the hyperbolic metric. So you took your point Zi along the way, remember it's iterative, and you measure the distance from Z0, and I assert that there's one when I apply G, I'm closer. Okay? And by its very nature, if you repeat this, because the group gamma is discrete, you'll end up with a discrete set of points in the upper half plane. Therefore, this algorithm has to terminate. The set of distances is finite. Once it's been bounded in any compact set, you only have finitely many elements of the group. So ZR equals Z0, and then you get a relationship just like we had before. Okay? There's optimizations for those of you thinking algorithmically. There are better ways of doing it here too. This is also kind of an order and checks, and there's also better way. You can find out which element to apply by looking in the unit disk and seeing what the angle is. Yeah, a math question.
Yeah, sorry.
What's up?
Sorry, this is a dumb question, but why does the stabilizer Z0 need to be tricky?
Oh, well, at the end here, you have an that's a good question. It's not, no questions are dumb. If let's say after all of this effort, I end up with, so I start with gamma, and then I have my bunch of generators, right? I start with Z0, and then I apply my gamma, and then I'm a Z1, and then I have all these weird generators. I don't know what they're going to be called, G1 up through GR. Okay? The conclusion that I have is this. So then, the product G1 up through GR up to G1 gamma, well, the conclusion is that this belongs to stabilizer. So strictly speaking, if you knew what the stabilizer was, you could say, hey, which one of the elements of the stabilizer you are, and then you would get you get equally well an identity of your group, so no bigs. But it's also, it's a bit nice, since you got to pick your Z0, nicer to pick with no stabilizer. Oh man, that was so much fun. You pumped? Any questions? Okay, now you own, bless you, finite index subgroups, that's up to you. Whatever pictures you want to draw, explicitly you want to work with them, you can. You know what they look like. Yeah.
So the input we take, we want a way to like easily identify whether the element is in gamma or not. So that's why Sage is not accepting, for example, if I give you a static generator for gamma.
Yeah, because it doesn't know if it belongs to the group or not.
Well, the most likely example is I give you the generator subgroup, right?
I know. That can be tricky though. Do you know how all of mathematics is, there are undecidable problems of that nature? So you have to be a little bit careful. If you promise me that your subgroup is something of finite index in SL2Z, then there is also an algorithm that will work. I'm sorry that it's not in Sage. But it goes like this. You just write out all the words of your group, keep writing them, and you compute something which is called a Dirichlet domain. So you keep track of all of the points that are closest to your favorite point in the upper half plane. Maybe it's 2y or something. So you keep writing, you keep writing, you keep writing. What ends up happening is you'll end up with, so this is your favorite Z0. So this is a way to get back to having tested. So you say, okay, maybe I wrote down an element of the group, and I want to take all the points that are close, it's this kind of inequality. I take all the points that under gamma are closer, the identity is closer than the G. So you'll end up with things that look like this. So you have all these elements, they are cutting out right pieces, and eventually they no longer contribute to the cut setting. And once you have that, you've constructed a Dirichlet domain, what's called a Dirichlet domain for the group, and then you still will end up with side pairing elements and all of the rest. Okay, so it's not a very simple algorithm. It's not designed for that, but there exists an algorithm that takes as input a set of generators of a discrete subgroup of PSL2R and outputs the wholly coordinate. Okay, What else? You guys have always good questions. You guys want to do some homology now? Modular symbols? Okay. Probably I have no time left. Yeah, typical. So we already saw how important it was to keep track of paths in the upper half plane as a way of understanding discrete groups, and the object which tries to keep track of those paths more than just for the fundamental domain, but with applications to homology and modular forms, is something called a modular symbol. Okay? So in other words, we're going to keep track of the homology class of these paths. They're not strictly speaking in the homology yet, because we don't know that they map up to loops, but they're homology relative to the cusp. We're going to draw geodesics in the upper half plane with bound endpoints along the circle at infinity. We're going to keep track of the group action on those paths, and the magistry is that tells us the information we want to know about our group, modular forms, etc. Okay? So take two elements, alpha, beta, and P1Q, this is Q union infinity. Okay, the modular symbol or alpha beta is, okay, well, people write it alpha beta. And that's confusing because you probably are thinking that that's a set, and I can't change that. If you want to, you can put underlines here, or dots, or make it green, or whatever, but you're just going to have to realize that it is not a set. The order matters, okay? The modular symbol, it is the, bless you, the homology class of, if you don't know about homology, you do not need to understand what's in parentheses. But for those of you who do, then I'm going to use that word because it helps you to understand what we're doing. Well, okay, you'll see what I mean. Path from alpha to beta in the completed upper half plane relative to the cusps. Okay, that just means to say that we allow paths with endpoints. In okay, what is the point that I'm taking here? Well, if I were to draw a path in the upper half plane between my alpha and beta, of course, one of these could be infinity, but this is the generic case. There are lots of ways of drawing paths from alpha to beta. That's the content of the word homology class, okay? There is a favored one. It's called the geodesic. Okay, so you can take that as your representative path, which is why that's not important. But maybe later on we're going to compose the things, and then we'll want to see that as being the unique geodesic. So you have to keep in track that this is also equally well a representative of the symbol alpha beta. In homology, you take loops, and I'm saying that you do not need to take loops. In fact, well, you can if you want to. Alpha and beta could be equal at this point, but I'm allowing you that not to be a loop, so it's called relative homology. Hey, probably my Dartmouth cohort, you have to suffer through relative homology. You have a complex, and then you have a subcomplex, and then you take the relative homology. Good times. Now, what can you tell me about, there's a homology relation. Again, for those of you who know homology, I'm saying that because I want to, those are the important concepts in topology that I want you to, for those of you who don't, just think about that word as being, I'm going to define each of the, what I mean. So homology relation is, well, if I do alpha beta and then beta gamma and then I go back, I haven't made a path. I have something which is homologous to the identity. Is declared to be satisfied. How about that? So for those of you thinking abstractly, I'm now making some enormous group generated by the symbols alpha and beta for alpha, beta in P1 Q, and I declare the homology relation star to be satisfied, and that is the picture. I could go to gamma, and then I go back, and I declare that to be trivial in my group. Okay? So let's make a Q vector space. Is that okay? Rather than a abelian group, it'll be easier with keeping track of ranks, and then we don't have to throw out torsion, which everyone always does. Okay? So we let M2. This is the space of modular symbols. Be the Q vector space. The basis the modular symbols. With the alpha beta in P1Q modulo the subspace generated by star. And that's okay. I mean, you could take an abelian group here, but then I'm not out by torsion. So let's take Q vector spaces. I take some really big vector space generated by a huge number of symbols, and then I have a subspace generated by these guys, and I take the quotient of those two vector spaces. Okay, so you can always think about it as actual modular symbols, modulo relations like this. Okay, how big is this thing? It's an enormous vector space. Okay, enormous. What else can you deduce from star? Well, I encourage you to prove that for any alpha, I have alpha alpha equals 0, and that alpha beta is minus beta alpha. See if you can prove that for alpha beta. Okay, that follows from star. Now, we are going to act on this enormous vector space by our discrete groups gamma. The fairy symbols and other coset representatives are going to help us to keep track of that action, and there's going to be the mystery. Okay, so we just made an object, a linear algebra object, that's going to keep track of our nonlinear group actions, and that's going to be awesome. Okay, so now let's have our group act. Everyone okay with our modular symbols, M2? Okay, how's it going to act? There's a natural action, right? If I take a G in my group, and I want to have it act on a modular symbol, you can act by linear fractional transformations on the alpha and beta, right? LFTs. You know me. Okay, so heads up, we're going to integrate along these paths. So that's the reason why we want to take some G invariants. Okay, so here comes all-important lemma. Perfect. So M2 is spanned by a special kind of symbol. By special kind of symbols, and these symbols are, I take the path from 0 to infinity, but I'm going to write it as infinity to 0, so make the argument a little bit easier. And I have gamma act, where gamma is in gamma of 1, SL2. So all of the alpha, beta on the planet, if I look at the symbol alpha, beta, I could have gotten that just by applying a matrix in SL2Z to the single symbol gamma 0. So in other words, if you want to think about this vector space as not just a giant vector space, but a vector space equipped with the action of this SL2Z, then it has a canonical generator, infinity 0. I don't know how canonical it is. It's canonical if you declare it to be. Okay. Now that's not obvious, this lemma. Okay, but it will be after I show you the proof. The proof is continued fractions, the Euclidean algorithm. That's good stuff. Okay, so first of all, if I take my alpha beta, I can write it as alpha 0 minus beta 0. by the homology relation. If I want to go from alpha to beta, I could go first alpha to 0, and then 0 to beta, and then I write that in the other way. Okay, so we show for, it's enough to show this spanning condition, we can show it for alpha 0. If alpha is equal to infinity, boy, are we all set. Otherwise, our alpha is in Q, and the magical step here is that you take the continued fraction for alpha and its convergence. Okay, so the first step in the continued fraction is just the floor of alpha, so that will give me some integer a0. This b0 is going to be equal to 1 because I just taken the floor there. Okay, and then I write out the other convergence of this fraction until I represent my alpha. You guys know about continued fractions? So you take the floor, subtract off the floor, plus 1 over the next thing, and then you get an integer, and so on, and that's another unique way of writing. Usually you do that in the context of quadratic irrationalities. You notice the periodicity of that continued fraction expansion that tells you something about solutions to Pell's equations in the fundamental unit. In a real quadratic field, I don't want to do any of that. I just want you to do it for a rational number right now. So this is a finite continued fraction expansion. And if you've never seen this before, you have lots of fun exercise periods this afternoon to go and read up on basic properties of continued fractions. You could think about the continued fraction expansion as coming from the Euclidean algorithm. So the convergence are related in that important way. That's why I also published that. So here's another important property of the convergence. So they satisfy this relation. Okay, so that's one of the things I'm going to ask you to check if you haven't seen that before. And now I'm just going to write out the relation in homology that comes from writing out the continued fraction expansion. Okay, that's just a trivial concept, not trivial, I hate that word. That is a consequence of the star fundamental relation, just because I wrote each term repeating each, so I just broke up the symbol, inserted it, divided up the path according to each of the rational numbers. But now the point is that because I have this relation, if I wrote down the matrix with these entries, there's determinant plus or minus 1, and even better than that, well, these are all integers, right? Well, I wrote down a fraction, continued fraction expansion, so I wrote them as rational numbers there. So you can write this as gamma n infinity 0 plus dot 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 plus gamma 1 infinity 0. And then I have to do a little of futzing around here to take care of the integers. But there, they'll serve with, so the gamma i's are defined in this way. They are ai. You have to take care of the signs to make it all work, but you can. Just take the negative of one of the columns instead. And then for this gamma 0, I make a special matrix to deal with the last step. Okay? So is that clear? I just wrote down the explicit matrices so you can see how you deal with the determinant minus 1. But the continued fraction expansion gives you adjacent fractions. Does it look like very simple stuff? Okay, they are all trying to tell you the same meta idea, and here we're seeing in a very concrete, efficient way. So if I gave you random alpha, beta, how hard is it to write it as a sum of symbols of the form gamma infinity 0? No harder than computing this continued fraction expansion. And if you read more, you can see how that's related to the Euclidean algorithm for a over b. So there's alpha, beta. After you write it as alpha over 0, I have a over b, and the fraction expansion probably over time. Yeah. Oh, not too badly over time. Okay, I'm not going to keep going. I just want to see what else is next. Okay, so next time we're going to take our finite index subgroup of PSL2Z, have it act on this space of modular symbols, look at the basis there. That is trying to tell you about the homology of the curve. The homology of the curve can tell us things like the genus, and more than that, finally there'll be some Hecke operators, and that will allow us to relate to modular forms. Okay, so thanks. That's all for today.